Hey there, in this video I want to talk about using scipy's Solve Ivp function to solve ordinary differential equations for us. And we're going to do an example, and it's one we've done before. It's the circle. So dx dt equals cosine y, dy dt equals sine x, and we had initial conditions x at 0 equals y at 0 equals 1. So we know ahead of time this is going to make a circle. We need to import the function we want, and it lives in the integrate module, because solving ordinary differential equations is a type of integration. You're adding up small changes. Okay, so the function we want is solve underscore IVP. IVP stands for initial value problem. There are two big classes of ordinary differential equations. There's the initial value problem, where you have initial values, initial conditions. That's the type we've been talking about. There are also what are called boundary value problems, and there's a Solve BVP that we'll talk about coming up in a future lecture. Okay, so let's look at how this thing works. And it's nice because we're not going to have to write so much code anymore. But it's a little, it's got its, well, it has its charm, let's say that. So if we look at the way Solve Ivp works, it wants a function. It wants something called t-span. T-span is the starting and ending time value you want. By default, this uses an adaptive method. So it picks the time steps for you, and you just tell it where you want to start and where you want to end. Why not is an array or some kind of sequence of the initial values you want. This thing will work just fine with simultaneous equations. We'll talk a little bit more about method in an upcoming video, but by default, RK45 is the fourth order Runge kata, where it plays some tricks with the adaptive part to make it effectively a fifth order method. But it's actually really similar to what we've been working on. And then the other one we might want to use here is t-eval. This is a sequence of time steps that you want. And well, let's just see how this all works out. Okay, so before we can solve anything, we need to have a function to solve. So we're going to define our f here. Now, so far we've seen the order be f of r and then t, where r could be an array of multiple values. In this case, r would hold x and y. As it happens, the way this function is written wants t first and then r. They hide it kind of down here, but if you go down to, it's right here. So you're solving the equation dy dt equals f of t and y. So it's kind of backwards. Watch out for that. And y is allowed to be an array. Okay, so in here, the contents of this will look pretty familiar. We want to unpack our values out of r to get our x and our y's. We want the fx, which is dx dt. That's going to be, just looking at our equations up here, that's going to be cosine y. And then fy, that's our dy dt, is going to be sine x. And then we want to return those. Before we had to put these things in an array with the code we wrote, it turns out that Solve Ivp is smart enough to figure that out for us. And so returning a tuple is fine. Any kind of sequence, it will turn it into an array for you. So we can save a little bit of typing. We don't have to wrap this in an array. It won't hurt if you do, but you don't have to. Okay, so now we're going to do Solve Ivp. We're going to give it our function. Okay, the next thing in our list here was the t-span, followed by the initial conditions. So our t-span is, I think we did 0 to 10. We got a little bit of overlap. So this matches our initial conditions here. So that's important. So at t equals 0, our initial conditions were x and y equals 1. That's going to be our next argument there. So that's also going to be some kind of sequence like a tuple, where I said I want them both to be 1. Okay, so they're both going to be 1 here. And that's enough to run the function. And we're going to leave this as the last thing in the cell, so Jupyter will just automatically print the results for us. And it's not just a number, it's not a graph, it's not an array, it's this complicated thing. Like, what is this? What did it return? So let's shove it into a variable called SOL, which is short for solution. Okay, and if we print or how about we just ask it, what is the type of the solution? The solution is this thing, an IVP ODE what? Well, so it's its own sort of thing. It's kind of like the minimize routines. They like return objects instead of just answers. Okay, and if we look at the help for these ODE results, like what are they? What do they have? Well, they have attributes X, the solutions. We have success messages, status messages. I mean, I think X sounds pretty good, right? So solution.x, what's that? Doesn't actually have an X, so it's lying to you. All right, so you really want to know how this works, you have to go look at the scipy documentation, or I will tell you, the actual attribute is Y, not X. Solution.y contains an array of arrays, or a 2D array in this case. Since we had two values here, X and Y, they're both packed in here. How do we get them out? Well, we can do tuple unpacking here. So X and Y equals solution.y. And now we can do things like print X, print Y, or in our case, let's try plotting them. Since we know it's supposed to be a circle, that'll be a good test to see if we got the results we wanted. There we go. It looks like a circle-ish. No, it's a hexagon. What has happened here? Well, it's picked the points for us. Turns out Rungakutta is like a really very accurate method. It didn't need a lot of points. Like every point is in the right spot, basically. But that's not what I want to plot. So what I want to do now is add another argument in here. This is that t-eval. This is, and if we're skipping method here, we want to make sure we give this thing a name. We want to make this a keyword argument. The way this works is, this is where do I want to see my results. So this would be something like a linspace or an A range. So let's say I want to see results from 0 to 10, and I want 100 of them. Well, okay. Now, finally, we got our circle, or at least a squished circle, but I think that's just axis scaling. Let's check. Yeah, so there we go. There's our nice smooth circle. Now, you can do weird things like, say, I want you to find solutions between 0 and 10, but I only want to plot solutions between 0 and 5. Like, that's legal, although it's kind of silly. Like, why would you waste the time solving to 10 if you're not going to use them? But, you know, just so you're aware, it's... you have to tell it what you want. Okay, now let's say I wanted to plot X versus time. Like I want to know what the time values were. Those are in here as well. They're the solution.t. In fact, I think if we do some tab completion there. Okay, so there you can see there's the Y. There is nothing named X despite the documentation for it, but there's this thing called t, which is what we want. That's all the time values. So we could do something like t equals solution.t, and then we could plot, for example, X versus t. Gotta tell it it's from Matplotlib. Oh wait, that's sideways. T versus X. There we go. And so that's, you know, not so surprisingly a sinusoidal function based on what we put into it. Okay. So again, this is how you use this thing. I mean, it was not very much code we had to write. That is its advantage. It's pretty slick as far as being really accurate. You do have a lot of control over it. But it's a little weird the way you call it. So watch out, in particular, things we talked about. The order of the arguments here. The independent variable has to come first. The fact that your result comes out as this object named .y is where your solutions actually are, and you have to unpack them if you have simultaneous equations in here. And if you want your t values out of this thing, you have to ask for them.